Thanks, everybody. As Rob said, you may not have heard of me today. My name is David Bianco. I will tell you a little bit. I find this a little bit embarrassing, actually. So I've decided that I'm officially announcing I'm changing my name to Rob J. Lee. So anyway, thanks for coming. I'm going to give a little bit different kind of talk than most of the other things on the agenda, and it's also a little bit different than the kind of talks that I usually give. I'm going to do something super micro-focused, and I apologize if there are people in here who may not be interested in this, but I think it's kind of an important topic. I want to, in my professional career, help people do better at finding bad things on their network and defending their organizations. That's my main career goal at this point. And as part of that, I run this side project website called the Threat Hunting Project. Threathunting.net, by the way, should be pretty easy to remember. And what I do on the Threat Hunting Project is I look online to find all the different places people are talking about how they do threat hunting, like what threat hunting things procedures they're following, what's working for them, what are they trying to find, how they're trying to find it. And I index them such that any one of you could go to threathunting.net and say, I'm interested in doing some threat hunting. I'm not sure where to start. What kind of hunts are out there that I can just implement? I can read about other people who did it and implement it in my organization. Or maybe I'm interested in finding lateral movement in my environment. What hunts do you have for me that have to do with lateral movement? Things like that. And as part of my index product, I go through and I kind of extract out the pieces of information out of the original sources that would let you know basically what this is about and if it's interesting to you. And then if it is, you can click through to go to the original source for full details. And one of the things I extract out of this is like the technical mechanisms that you need to be familiar with to do the analysis piece. And many of these, most of them, have something to do with finding the outliers inside your data, the odd data points in this sea of data points. And I noticed as I was going through there that we are apparently not very diverse in our mechanisms for finding outliers. In fact, almost every single thing that I have in there that needs to find outliers uses the same outlier detection mechanism. And it's a good mechanism for certain things. It's not good for certain other things, but we try to use it anyway. And so I thought maybe what I would do was spend my time, instead of talking about like macro views of why do we hunt, how do we hunt, I wanted to talk a little bit about how we can do a better job in that specific piece of the threat hunting, which is finding data points that are somewhat unusual for some reason. So I'm going to talk about several different techniques, some of which are not new to you, some of which might be new to you, one of which is almost certainly new to you. And some of these things that you may have seen. You may have learned some of these in high school science, for example, but maybe just a reminder of the technique, some points about when you could consider using this technique and when maybe you should consider doing something else. And even in all of these cases, I will show you a little bit of implementation of that mechanism in usually Python. But don't worry, it's not a coding challenge. It's mostly there for later on when you want to come through and read the slides after after the conference, you will have a tiny, tiny bit of source code. Right now, today, I just want you to kind of look at the size. Like, none of these really require very much coding at all, but they can be really useful for you. So the first technique that we've seen already today, so Michelle and Maxime mentioned some things about it in their presentation earlier. It's called least frequency of occurrence analysis. We also, it's probably much more well-known in this industry, in this room, by its other name, stack counting or stacking. Who does stack counting? Everybody should raise their hand. The trick is the lights are shining in my eyes, so I have no idea who raised their hand or not. But the basic idea is really simple. You just take a data column that you're interested in, and you find all the unique values in that column, and you count how many times that each unique value occurs, and you sort by that count. And so here's an example that we have a synthetic data set from CertCC's insider threat data set that basically just says, here's some counts of the files that people have read. Show me the ones that people don't read very often. Like, maybe that's a suspicious somebody going out and just gathering lots of data that no one has ever accessed, but they're just sucking it all up, right? And you can see we start with like a bunch of ones that only one person has read, and then we get up to a few that a couple people have read. And it's really simple. So here's the first of our code fragments. This one is so super simple that it is basically in almost every kind of database system or threat hunting product can do stack counting. So in the first, you see just regular relational database SQL. It's basically group by and then order by. But you can do this in Splunk. They have this easy way of doing it. The Python has an easy way of doing it. It's not really complicated. It's really easy to understand, and it's really easy to implement, which I think is really why it's so popular. So, but let's look at some of the use cases why you would want to use this, and maybe somewhere maybe you should try to do something different. So first of all, yeah, obviously, we're stack counting things. We're looking for unique values. So this kind of implies that the things that you're looking at need to be something where you can actually look at enumerated types or categorical values or strings or something where there's not like an infinite number of different values in there, right? In our case, we were looking at file name strings. So it's pretty easy to say in this set, how many different strings do you have? And then count them all, right? It also works best when rarity is suspicious, which is not always the case. Sometimes, many times, rare values are just normal things hanging out. But when you do something, I think Michelle was talking about rare HTTP user agents, which is actually, like, I think one of the classics of threat hunting. Rarest HTTP user agents, check those out because they might be somebody who has installed a program that they shouldn't have, or it might be a malware author who has made a mistake in emulating an actual user agent. And rarity in that case may very well be suspicious. We also saw, by the way, kind of the opposite of this analysis technique when, I'm sorry, I forget if it was Maxime or Michelle were talking about building the baselines, where they actually did the opposite and they looked for the most frequent occurrence. So high frequency occurrence analysis. They said the most common things are the least suspicious, right? It's basically the exact same analysis technique with just like the greater than sign flipped for the sort. Now, this has some substantial weaknesses, though. First of all, I think it's kind of obvious, like when you're working with non-categorical data, like numbers. Numbers don't tend to stack count very well. Some things that look like numbers, like TCP port numbers, may, but they're not really numbers. It's also a little bit more difficult when you get into more than one data point or data field per data point. So it's possible to say, for example, stat count on multiple columns of the same row, but the more columns that you add to that, the harder it is basically to do that stat counting. But the last two things here on the slide are the ones that I think are the most critical weaknesses of this approach. First of all, it's hard to take that stat counted thing and turn it into an automated detection. One of the things that I'd like to see out of threat hunting is the drive toward automation of successful hunts. Maybe we won't always get there. And this is an example of where it's going to be hard to get fully automated. Mostly what people end up doing with stat counting is they put them into dashboards. And that long tail of results in a big data set, you're going to get a lot of rarities. I say, use this when rarity equals suspicion, but in fact, rarity usually does not equal suspicion. Rarity might be one small indicator of suspicion, but in a typical enterprise, there are maybe hundreds of unique, for example, HTTP user agents, but most of those hundreds are actually legitimate or at least benign, not things that you care about. So you could potentially have a long tail of results to go through here, and it's going to be hard for the automation to kind of help you weed those out just with stat counting. Now, having said that, there are certain circumstances, I think, which are great for stat counting. So here at the bottom of the slide, I have probably one of the ones that is an almost perfect fit for stat counting, right? I've never seen this service on any of my devices across my large network. And so therefore, if one or two or three of them come up with a new service one day, that's kind of suspicious and I want to know about it. So think about this when you're thinking about whether you should use stat counting. How close does that sound to a problem statement like this? If it's really close, it might be a really good way to do your analysis. The farther it gets away from that kind of statement, though, the least likely it is that stat counting or least frequency of occurrence is the thing that you should be doing. Now, the next couple I want to talk about are visualizations. So maybe not intended entirely or really directly for automation, but they're part of the analysis process that will get you to be able to figure out how to automate this, right? The human brain is really, really good at taking in a lot of data visually and making a quick decision about that. Chris Sanders is somewhere in here. He's our industry's expert in this now, I think, and he can probably tell you a lot about this. I'm not pursuing my PhD in cognitive psychology, so I will defer to him, but I think he would probably agree with me that one way to kind of get the full brain engaged in making some of these outlier decisions is to show things visually. We are very good at it. Look at that piece of toast and tell me what you see. No, I mean it. Tell me what's on that toast. Yeah, I hear Elvis. Yeah, and if you didn't see Elvis, you probably cannot unsee Elvis now on that toast. Our brains are so hardwired to find patterns and that we can literally see Elvis on what is actually random toast, right? And the best thing about that is when we are so good at finding the patterns, it kind of implies that we have some ability to find the pieces that don't fall into the pattern as well. So let me talk a little bit first about just the basic scatter plot. I think the basic scatter plot does not get enough love in the threat hunting community. Alex Pinto talked about this particular plot earlier during his presentation. He mentioned it briefly. He said he really liked this example of threat hunting. This is, I won't go into the whole thing. I tweeted the link to the blog post that this was taken from earlier if you want to read it. But I'm basically looking to see who might have changed which hosts on the network might have changed their ratio of bytes that they send to the internet versus bytes they download from the internet, as a way of looking for who's acting oddly and maybe starting some data exfiltration, right? So what I've done is I basically computed they call it the producer-consumer ratio metric for each host in the data set. And then on one axis, I have last week's value, and the other axis, I have this week's value. And if there's no change, they fall along this diagonal line right in the middle. And you can see there's a number of hosts that fall very close to that line. Most of them fall kind of close. But visually, you can kind of see some outliers. And I have highlighted them a little bit by color coding them. So the more positive they are, the more data they've been sending to the internet, the more red they are. And the more data that they changed receiving data from the internet, the more blue they are. I'm, in this particular case, not concerned with the blue data. I'm more concerned with the red data. So it happens that the most red host jumps out at you pretty easily just by looking at this thing. And it would not really be an easy thing to do just looking at a column of numbers. Yeah, you could sort the column of numbers, but it doesn't really give you as much of an idea of how different it is and whether you should really care. Because there are a number of ones that are over or above, over the line or below the line, but you really need to know the magnitude as well that they're away from that line. So just engaging the brain a little bit to look at it visually a lot of times is the right thing to do and can save you a lot of analysis time. Just as a simple example, I've been using this Python library called Plotly. So I like the way it makes its graphs look, and it's pretty easy to use. And you can see I've got it, basically, I did that thing in like 6 lines of code. And it's only 6 lines, really, because I tried to make it readable and separated things out. You could actually combine all this into like 1 line of code if you wanted to. So it's actually pretty simple. I'm not going to go into all this in detail, but it basically just says, here's one axis of data points, and here's one axis of data points for the other axis, and then plot it. That's the basic idea there, and most of the other things are making it look pretty. So scatter plots, then, are most useful when you have, first of all, obviously numeric data, right? Not going to help you if everything is a string. And usually when you have 2 sets of numeric data that you want to compare to each other. They're most useful in 2 cases. One where your hypothesis is such that malicious activity will violate some clear visual correlation. In my case, it was they fall on a line, but there may be other cases where they are a curve, or you would say everything should cluster into, say 3 main clusters of points on the graph, and you're looking for things that don't fall on that line or that curve, or that are clearly far from any other established cluster, things like that. So that's the first use case where it's really good at. The second use case is actually when you're not sure if there is a correlation, and if there is a correlation, what it might be. It's actually really nice to just be able to say, are these things correlated at all? I don't know. Let's put them on a scatter plot. And if we see a line or a pattern of some sort, we can engage that brain to identify what that pattern might be. And if there is no pattern, you'll see, most likely a random distribution, like static on an old TV channel. But of course, like all of these, it has some weaknesses too. First of all, I already said if you're not working with numeric data, you're probably not going to be doing a scatter plot. It also is kind of weak if the correlation is not really a fairly strong correlation. If it's a very weak correlation, it may not be as easy to find the outliers. Say instead of a line that they would fall under, if they were in a wide band, right? That correlation might be kind of iffy and weak, and it would fall apart at the edges of the band, so it would be harder to find out if things were actually in that band or if they were outliers, because not a strong correlation. And The other big weakness is maybe you have data that needs to be compared on more than 2 axes at a time. So if you do data analysis and you have a lot of different fields, it's actually common to take all the different fields in combination and do a matrix of scatter plots so you can see which fields correlate with each other. But that's not what I'm really talking about here. I'm talking about if, for example, you have 4 lines of data that need to all go together. You can't really do that easily on a typical scatter plot. In this case, again, think of it like a near perfect case for scatter plots would be what I have here. Most users don't change their upload habits, so benign activity should fall close to the no change line. The closer your problem statement is to that model of a problem statement, the more likely it is that you would find a scatter plot to be useful to you. So now let's talk about something maybe some of you have not really dealt with very much. The box plots are also called box and whisker plots. Box and whisker plots are really interesting because they get you a visualization of the distribution of your data, the shape of that column of data, as well as they actually show you some information that you can use to later on, after you're done visualizing the problem, compute the outliers in the data set. So, and you'll see here we have 2 different versions of it. So let's talk about the blue version here on the left first. What I've done is I've taken a data set of command line lengths for processes that were either command.exe or PowerShell in an environment. Like my hypothesis for this hunt was, especially with PowerShell, commands, like attackers trying to live off the land and use PowerShell things in my environment to do their dirty work tend to have like long lines that have PowerShell scripts basically built into them. And so I'm interested in knowing whether I think I could use that length of the line as a possible indicator of maliciousness. So the first thing I wanted to kind of do is find out, what does that distribution of that data look like? I have a bunch of data points. I'm not sure if this is a thing that I should be looking for or if it's a good enough indicator by itself. So what I did was I created a box plot of it all. And you can see I even have a scatter plot built into this box plot to kind of show you how the box plot actually shows the shape of the data. So first of all, it starts with these 2 whiskers. And that's really what they're called. That's their technical name, the whiskers, right? It's the minimum and the maximum things in that data set. And just pay attention to these 3 lines here that make up the box. The bottom line is the line at which 25% of the data points fall below that line. The 25% line is also called the first quartile. But I rarely call it that because I can't remember complicated statistics, things like quartiles. The middle line here is the line at which 50% of all the values fall below it. And does anybody remember what that's called from high school? Yeah, it's the median. So if this is 25 and 50, what do you think this is? The 75, the third quartile, right? Technically speaking, by the way, they call the box from the 25 to the 75 line the interquartile distance. I don't know why you need to care about that, but I'm mentioning it anyway. And then you have here this top. If you read about box plots online, they will tell you usually that this is the minimum and this is the maximum in the data set, but in fact, that's not entirely true in this case because we've actually computed, look, there's the max, right? The 100% of the data is supposed to fall below this, but we have something up here. The outlier. So the cool thing about the box plots is the box plots actually have these whiskers that tell you this is the high outlier or the low outlier threshold. And the reason I like that is because as you visualize this, then it actually you can read right off the line, well, here's the threshold that I should automate against, right? Like if it's above this, we'll call it an outlier because in my sample data sets, everything should be within the 2 whiskers. So we have a high outlier here. There's another version of the same box plot. I did not put the scatter plot on here. This orange one gives you a tiny bit more information. The middle dotted line here is actually the mean. So spoiler alert for high school math, the median and the mean are not the same. Sorry. I know some of you are just waiting, you're queuing those textbooks up to read later. Sorry, I spoiled it for you. But the reason that that's interesting is because using the mean, you can compute the standard deviation. Does anyone remember that's not Alex Pinto what the standard deviation is? You can just yell it out. Yeah, I kind of heard a little bit. It's actually, if you take all the data points in the data set and you compute their distance from the mean, and then you average all those up, you find the standard deviation. It's the average distance of each data point from the average. And the reason that that's also interesting is because, and this is kind of a bonus tip that I didn't really build into the slides, it's actually a really common thing to say, my outlier filter is, say, 3 standard deviations away from the mean. Anything above 2 or 3 standard deviations is an outlier. And in this case, it's actually close to 2 standard deviations. It's not quite, but it's actually close to 2 standard deviations that it computed the outlier threshold. So it's just a little bonus fact. And you can get the standard deviations at the same time you do the box plots. So. And again, just like the other ones, also with Plotly, I didn't really have to do that much. The main thing is here where here's the list of all of the data points in this array here. It's actually a pandas data series, but basically Python doesn't really care. It's just a list. And all this stuff is just like making it pretty so I can put a title on it so I know what it is later on. And so it's actually not really very difficult to make this box plot either. So the box plots are really good at when you have numeric data, first of all, right? It needs to be numeric. And I used a big term on here to make myself sound smart, univariate, which basically just means one variable. You have one data column that you're dealing with. So if you have univariate numeric data, and you want to get an idea of the distribution of that data, a box plot might be really good. It's a quick visual representation of the data shape, and it'll also do what we call the skew. Like, it'll show you visually if most of the things are at the bottom of the range or the top of the range, or if they're evenly distributed, things like that. And the outliers are explicitly shown, anything that's outside the top or the bottom whisker. And you can take those and read them right off the graph and say, now I know my outlier threshold should be 4.7. So I'm going to put it in my Splunk query or whatever when I compute this metric, and if it's greater than 4.7, fire an alert or do whatever you're going to do. Though the main weakness of it, though, is that as a kind of high-level summary, the box plot, without all of the scatter plots on it, kind of loses the individual data points. I don't usually think that's a big deal, though, because I'm just trying to figure out the shape of it. But if you have a lot of data points, it's hard to generate that scatter plot on a regular laptop or a computer. So. And again, here, I don't know what's normal for this column of numbers, let alone whether there are any outliers in it, but I need to find it out. If that's your hypothesis, looks like that, this is probably a good technique for you to use. All right, first of all, take a breath. We're done with visualization, right? No more graphs. I know it feels like you're back in high school, maybe. The bad news is, now I'm going to talk about something a lot cooler. and maybe conceptually a little bit more involved, but I'm going to try to walk you through it. The payoff, though, is that I get to join the ranks of the people that get up here on stage and talk about machine learning. It's a payoff for me. I didn't say it was a payoff for you. So, and I'm not going to tell you that this is the only machine learning you can do to find outliers. It's just a cool one, and it's something that I work with occasionally, that a friend of mine from Squirrel, actually, their chief data science, Chris McCubbin, introduced me to. It's called isolation forests. And remember I talked earlier about the scatter plot. One of the possible things might be clusters of data on the scatter plot, and you're looking for things outside the clusters. Great for, and you're looking at it with your mind or your brain, and your mind can interpret all that. But not so great, how do you interpret that if you're a computer? This is a technique that you would do to automate finding things that are not part of clusters. It's a form of unsupervised machine learning, basically meaning the machine does not have a list of things that are known good and known bad to go by. It's actually just saying which things are different from the others without really having context or giving you a strict interpretation of what that difference means. It basically says you have a big data set of data points. And these data points can be two-dimensional, so like we have here on the graph, or they could actually be multi-dimensional. You could have 10 or 20 dimensions, more than that. It's hard to visualize at that level, so we're going to show you on 2 dimensions, but it actually works with many more dimensions on that. What you basically do is you find a random data point, and you take that data set, and you find a random dimension and a random value within that dimension, you make a split. You see they've done that here. And you basically are saying, like, everything above it is on one side of the split, and everything below it is on the other side of the split. And you do that again. You pick a data point on one side, and you say, OK, I'm going to make another split, random split on random value of random dimension. And you keep doing that. I'm going to make this split, then I'm going to work with everything over here. I'm going to make a split. I'm going to make a split. I'm going to make a you get focused down. And they make this is called a tree. Basically, this record of all the splits you took to get to each data point is a tree. And you're going to split all the data points in that. You do that a bunch of times as well. So because this is random, you split all of them until everyone has been split, and you have a record of all the splits to go to each data point. And then you start over and you do it again, getting different random choices each time. And you do this a bunch of times. You generate a lot of trees. That's why they call it a forest, right? And then basically what you do is you end up with a bunch of trees that for each point, they have a depth of how many splits you had to do, random splits you had to do to get to that point. You average all those, and you say, well, for this point, the average depth is 2, or the average depth is 24. And if you think about this, this tells you how close it is to other data points, because the lower your number, the fewer splits you had to do until it was isolated into its own area. That implies that it's probably farther from all the data points, because look, I mean, this guy had to do basically, probably one split or maybe a few splits, depending on how the random things went. These guys, we had to do a lot of splits to get to, right? So you can see this is things that are really close to the rest of the cluster. They're the inliers, and these things are kind of the things that are really far from the cluster. They're the outliers. Now, this actually is something that Tim Crothers mentioned this morning in his ML presentation. So Chris McCubbin and I have this demonstration tool for finding odd bro HTTP logs, and I put it out on GitHub. It's called Clearcut, and it uses 2 different algorithms. It does a random forest, which I'm not going to get into here, and then it does the isolation forests. So rather than paste the code in here again, I would just say go and look at the Clearcut code. It is designed so that it is a reference implementation, basically simplified, so that you can see the steps of how to implement isolation forests in Python with scikit-learn. It's not very difficult. The harder part is doing what they call the feature engineering, like looking at all the data points and converting non-numeric data into numbers. But the actual implementation of the isolation forest is built into scikit-learn, so it's just some API calls. So when might you want to use this? Well, it has some strengths. The first one is when you have a lot of different columns in your data. They can be numeric columns or possibly things that can be converted into numbers, such that unique strings might be numbered so that you have strings 1 through 5, and you'll just put 1, 2, 3, 4, 5 in there instead of the actual strings. And it can accept a pretty large number of those columns per data point. The dimensionality can be pretty large here. It's also, it's a form of unsupervised clustering, but it tends to be a pretty fast one compared to other ones that like data scientists and hobbyists like me like to throw around, like k-means clustering or something like that. This is actually pretty fast. You can get good results on a reasonable data set with like a laptop. You don't need a lot of hardware necessarily to do this, and low memory requirements as well. But to me, probably the best use case of this is you can use this and then you get to say, yeah, we have a machine learning solution for that. It's a little bit weak because in the sense that creating those features, deciding which the features are important, and converting non-numeric things into numbers is not really rocket science, but there's a lot of work kind of involved there. And it's difficult to visualize this at high dimensions. You can do 2 or 3 dimensions pretty easily, and then afterwards, if you wanted to see what the output was, to understand it a little bit more, it'd be kind of difficult to show it in 4 or more dimensions. But good thing is that's not always necessary. And so here's an example, and this is directly from our Clearcut implementation. Which of these HTTP log entries are most unlike the others? So we took the typical bro HTTP log and featureized it. I can tell you offline if you're interested, like what kinds of things we were looking for, but we converted them into a set of numbers for each line in the log, and we ran isolation force against them and showed the ones that were less like all the other ones. It works out pretty good. So your brains can relax. We're done talking about machine learning. But I want to sum up by saying, if there's one key takeaway I would like you to have, is don't just automatically jump to stack counting. Sometimes that's useful, but you have a lot of options. You can do stack counting, least frequency of occurrence. You can do scatter plots now. You know how to interpret Boxplots now. And you could even bust out some machine learning and impress your boss and get a raise. And these are not the only ones. These are just like 3 common ones and then 1 interesting one that I threw up in here. There's tons of different options, and please don't be afraid to play around. Get out from under the stack and go do play with some other ways of finding the outliers in your data and see if you can achieve a better result or quicker time or both.